Hello, I'm Simon.
And I'm Magnus. This is our topic. It's pollution-free transportation. In our case, we were looking at magnetic trains. These are called maglevs, which is an abbreviation for magnetic levitation. Our purpose is that we want to improve public transportation over large areas because maglevs are very fast. They can go up to over 500 kilometers an hour. And they use power that could be green energy from windmills or solar plants, and they use instead of using polluting fossil fuels. And our hypothesis is we want to find out how to build a magnetic train, what it would require, and how fast it can run, depending on the voltage provided. We suppose that the speed will increase as the voltage increases. I'll tell you a bit about electromagnetism, because that's what we're using for propulsion. If you send a current through a wire, which I can show you here. If you send a current through a wire that is coiled around something, if the current is flowing towards you, the magnetic field will go counterclockwise, and the opposite way around if it's flowing away from you. The magnetic field is used in electromagnets, and this is an electromagnet. It's called around a magnetic core. That is usually from iron, nickel or cobalt. Ours is iron. And the magnetic field is then concentrated inside the coil, which makes the metal magnetic. The metal core is added because the atoms in the metal works like a lot of tiny magnets that all point in a different direction, that at the end add up, even out. The magnetic field makes the atoms point in the same direction, making the metal magnetic. Electromagnets are smart because, unlike permanent magnets, you can control them, how strong they should be, and when they need to be turned on.
Then we would also like to tell you something about capacitors. And capacitors are the small electrical devices that you see here, and we've also tried to cut some of them open. And if you look inside a capacitor, you'll see two plates of good conductors, usually a metal, and those are separated by a dielectric, a small space between them that can't conduct electricity. So when you, for example, connect it to a direct current, the positive will go inside one of the plates, and they will take some of the free electrons from that plate, and they will go around and into the negative plate, because electrons will always try to go from positive to negative. And soon after, we will have pumped all the free electrons from one plate over to another, and we can't pump any more. And that means that we have a negative plate and a positive plate, and those will be attracted to each other. And that will hold the current inside it for a while, depending on how strong it is. So if you connect it to, for example, a ball, you will see that it's slowly lacking out of it, and after a while it will die out. However, if you connect it to an alternating current, it will never actually pump one of the plates full, because alternating current is always changing direction. So it will pump some of them over here and then some of them over here, and will never stop. And instead of working like this kind of battery that we're using it for if you're connecting it to direct current, we can use it as kind of a resistor. And this one here that we have used in our experiment here, it's kind of a special one. It's an electrolyte capacitor, and it's built up in a special way. One of the plates is made of aluminium foil, and it's corroded rough, so it will have a huge surface. And then it's treated with oxygen, and this gives it a layer of aluminium oxide, which works as a dielectric. And then you can see the spiral here. That's electrical needle paste, and that's the other plate, and it surrounds all the aluminium and goes into all those small holes that you have corroded. And that's why this is so effective and has a great electrical capacity. Because first off, because the dielectric is small, but also because that the surface area is really big. However, there's also some disadvantages for this electrolyte capacitor. It can't take that much of a voltage, only a few hundred, where others can take up to 1,000. And the plate with aluminium foil needs to be connected to the negative. Otherwise, the aluminium will begin to decay, and after a while it will have decayed, and it will short circuit itself and potentially blow up actually. Then there's also something about magnetic flux, which in a second we will show you how this actually works. But magnetic flux is when you have a magnet. Humans don't quite understand that actually, and therefore they have made those, they call them lines of flux, to illustrate how a magnetic field works. And if we say, we take this magnet, and my hand is now a metal plate, then the lines of flux will go from north to south, and they will at some point penetrate the metal plate. And some of them will go through, but other ones will be absorbed by the metal plate, the surface. So if we suppose that there are 10 lines of flux, and 5 of them are going out on the other side, 5 of them will have been absorbed by the metal plate, and that means that I have a magnetic flux of 5. That's also the principle that we use here.
What we're doing is we're placing this Coca-Cola bottle on this metal spike thing, if I can place it. And then we turn on the power. This is 2 electromagnets. And then the bottle will start spinning because it's magnetic flux.
Those will simply send out a magnetic field, and the magnetic flux that is building up will push on. But we need to have kind of a delay from one of them, and that's why we use the capacitor. Because as I said before, when we put alternating current into a capacitor, it will be used kind of as a resistor. And if we look here, naturally from the inductance of the coil, the current will lag behind the voltage. However, the coil that we have connected to the capacitor, inside that one, the current lags less behind. And that means that when that one has peaked, then the other one will peak. And they're pushing in that pace, making it turn. But propulsion isn't the only thing that makes this train work. We also need to levitate it, magnetic levitation. And that's the thing that actually makes it really fast, because it has no friction between the train and the track. And for that we have used those neodymium magnets. And those are a kind of rare earth magnets that are really strong. And they are made up by neodymium, iron and boron. And they are in this special structure that make them really hard to demagnetize and really strong. So if we see here, and they face the same polarity, they will always try to turn around and smack together, because they're that strong. And actually the only thing that can make them less strong is if you're heating them up. At 80 degrees Celsius they will begin to lose strength, and at 310 degrees Celsius they will completely have lost their strength. If you've tried to buy some of those neodymium magnets, you will also have seen that they have this special kind of rating system actually, that shows you how strong the magnet is. Usually you can go by the rule that the higher the number is, the stronger the magnet is. So those ones here, they are N35 to N45, which is quite a lot, because the strongest one is N52. So if we're showing the actual thing that we made here, you can see we've actually done pretty much the same as I just showed with the two magnets. We've made those face upwards, and then the same polarity facing downwards on the bottom of the train here. Which will make it levitate when I do like this. And there's actually a hole here. I don't know if you can see that. And it levitates over it.
So, this is, of course, an experiment. There are two different kind of maglevs. You see here, there's the German one, and that's the Japanese one. We've modeled ours after the German one, because the Japanese one is very hard to make in small scale. As you see here, this is the principle the German one is using, with an electromagnet here to do the levitation, and here for guidance and propulsion. We have these as guidance as propulsion, and instead of electromagnets that levitated, we've used neodymium magnets facing the same polarities to each other, which didn't work so well, and it kind of sometimes falls off the track and is a bit unstable. But so that's our problem with this, that it isn't that stable. But as you see, it can run, kind of, but we didn't, these are too large. So, but it can kind of run, and it is levitating. There's nothing holding it up, other than the magnets. And then, of course, you can see all this, the track and the train we've made out of 3D printed objects. These are made with a 3D printer that heats plastic up to 210 degrees with an extruder. Then it prints with 0.1 millimeter precision.
You can see here how precise it actually is. It can make all those small things on the boat here.
But 3D printers aren't very fast. They're very slow. The average for all of these objects we printed is 12 hours per object, which is a very long time. These objects are printed with this that is on a roll, and then rolls it into the extruder. And as you see here, the printer makes it in a specific way. We've chosen to make it 20% plastic, and then we'll make like kind of structure inside it to make more air, and this actually makes it stronger than if it was to be 100% plastic. Why we have printed it in 3D was because we wanted precision and modular. As you see here, it's modular, and you could just take this off and put it back on. We also couldn't make it in wood or any other materials because precision. And how we made it? We started by printing the objects for the experiment, which was the longest process. Then we drilled the holes for the neodymium magnets, which are these. On the track we have a 30 millimeter between each magnet and on the train. If Simon can help me take that off. We have a 15 millimeter different from center to center. And then we drilled holes in the track to make space for the electromagnets. And that's with a 4 centimeter difference from center to center. Then we assembled the whole track, all of this, and the train. Then we put a nut on it with 1.5.
You can see here that the space from the bolt head to the nut is 1.5 centimeter.
We made it with 1.5 centimeter, as he said, and then we coiled copper rod between those two areas. Then we removed the nut and we mounted it in the track. Then we place the neodymium magnets on top here and on the bottom of the train, of course making sure the poles are facing the right way. Then we connected all the electromagnets in series. As you see here, these black ones are the not connected to a capacitor, which is one of these. As we've done here, one of these are connected to a capacitor, which is this one. So 4 of them, we've put series of 4. 4 of them are connected to a capacitor, and 4 of them are just connected to the power source. And the same we've done here, these ones are connected to a capacitor, and the other ones are not. And that we've done that 4 times, all the way to them, on this 120 centimeter long track. Then we placed wheels on the arm because we realized that we couldn't get it stabilized because of the neodymium magnets. So we placed some wheels to stabilize it, but it doesn't help the levitation. And then we turned on the power and yes. And then for our results, we managed to build the train and saw what it required. However, we did not find out how fast it was, depending on the voltage. Therefore, decided to make a test of temperature instead. Why we did that was because the electromagnets heated up too much that it would actually melt the track if it was at the correct voltage. So we took this one to test how hot we can get these. And we got them up to 250 degrees Celsius. And this began to smoke, and this wire has some lacquer on it, which also
began to melt off.
Yeah. And then we tested the track, where we connected it all, and we, as you see here, we took 3 tests. We started at 24 degrees, and then it rose rapidly to 80 degrees, about 80 degrees, and then it steadily rose to 130 degrees, the maximum we calculated. And after 4 minutes with 130 degrees, the track started to melt because it's plastic. So our conclusion is, our experiment didn't work. But we managed to make the train levitate to some extent. However, the propulsion in our experiment based on the coils got so hot they melted the track. They were putting before building up the correct amount of flux, magnetic flux, to push the train.
So as you hear, our experiment didn't work the way we wanted it to. So specifically, the thing with the plastic track melting was a failure. So we think that, well, if we should do this again, we would try not to make it in plastic. As a prototype, it would be okay, but otherwise we'll maybe try to make it in aluminium. Then we would also like to make the electromagnets a bit longer, because the reason that they get so hot is because there's not enough turns on the electromagnets. If they're longer and have more turns, the heat will they will not get so hot. And we would also like to, instead of neodymium magnets, which again was kind of unstable, we would like to use electromagnets, turning on and off a lot of times each second, as they do with the German one here. And yeah, that was our experiment, and it was not just us doing it. There was a lot of people helping us, and we're very grateful for that. First off, Helmholtz AS, they helped us with professional advice and providing us materials, both the 3D prints and copper wire and so on. We would also like to thank Jesper Vedsholt for providing support and materials. We would like to thank Jesper Helmholtz for drilling all those holes you see in the track. That took quite a long time actually. And to Hilmer Helmholtz, which is really good in physics and could help us and pass on some knowledge that we couldn't get ourselves. And thanks to Henrik Helmholtz for helping us just all the way. And Michaela Gugu, our teacher, for telling us how we should do everything and make a report and make an experiment. And thank you to Ellen for helping us as well. And to Asgerbo for actually telling us how magnetic flux works.
That was our presentation. We hope you enjoyed it. You can come up here and ask us questions if you want and see this one go again.